In this last chapter, we're going to be looking at just solids and liquids. So in chapter 11, we were looking at just gases. So now we're going to look at just solids and liquids. So we're going to be talking about the interaction between the molecules in the solids and the liquids. So just a review here. Solids and liquids have high densities. Liquids have a definite volume, but they do not have definite shape because they take on the shape of their container. Solids have definite shape and definite volume. So we learned that a while back, but just to remember. And we're going to be talking about the interaction between the molecules and what holds them together. So intermolecular attractions or intermolecular forces are responsible for holding the molecules together in a liquid or in a solid. The distance in the gases really prevents intermolecular attractions taking place. They can, but because of that distance, they're not very important, so we're not going to cover those. We're just going to look at those in liquids and solids. So knowing the structure of the liquid and the solid really helps us to understand the strength of the intermolecular attractions. So we'll be talking about that and looking at different types of the attractions. So covalent bonds and ionic bonds are considered intramolecular forces. So that's different. Those intramolecular forces are very strong compared to our intermolecular forces. And just to give you an example here, okay, we have HCl. This bond right here is a covalent bond. It's an intramolecular force. But if I have another molecule come in, because I have a whole sample of HCl, okay, we're talking about the interaction right here. This is the intermolecular force. So we're talking about the interaction between the molecules. So intramolecular forces are much stronger than the intermolecular forces. Okay, so even though intramolecular forces are stronger, intermolecular forces are still strong enough to determine certain properties. So like melting and boiling point, freezing, condensing. So they're weak, but they're still strong enough for those properties. Okay, so first we're going to talk about the different types of intermolecular forces, and then we will look at how those affect the properties. Okay, so here we have, first up, dispersion forces. So let's imagine we have a balloon filled with helium atoms, and let's say one of those helium atoms, their electrons happen to end up on the same side of the atom. So helium has 2 electrons. So in frame 3, we see that both of those electrons are on the same side. And so we create this partial negative and partial positive. Okay, so let me draw this here for you. So here's our, let's try that again. Here's our helium atom. Okay, we have the nucleus here, and we have 2 electrons ending up on the same side of the atom. And so when that happens, since electrons are negative, this side becomes partially negative and this side becomes partially positive. And this is called an instantaneous dipole. Okay, so again, that's when the electrons happen to be on the same side of the atom or the molecule, creating that dipole. So the dipole goes in the direction of the negative. Okay. So if I get an instantaneous dipole, then eventually another atom's going to come in, and it's going to get close to that atom with the instantaneous dipole. Okay, so let's just say here's another helium atom. Okay, the electrons, I'm going to put the electrons in a different color. Okay, the electrons are on the opposite side of the atom, but as it gets close to this atom, what's going to happen is it's going to repel those electrons to the other side. Whoops, let's erase those. Okay, so they repel to the other side. And now we're creating another dipole. Oh, wait. Sorry, I did that in the wrong direction. Let's try that again. Okay, repel. And they're coming this way. Because really, I wanted to draw the electrons on the other side of this atom. Okay, so let's just back up here. Put the electrons on this side. The dipole. Okay, sorry about that. Dipole going this direction. Okay, so now they're going to repel those electrons over to this side of the atom. And now we get the negative, partially positive side, the dipole going in this direction. This is called an induced dipole. Okay, so the instantaneous dipole causes the induced dipole. And so now the attraction takes place right here between the partially negative and the partial positive of the two atoms. So dispersion forces occur in everything. Okay, doesn't matter if it's polar or nonpolar molecule, dispersion forces are in everything. And we can see some factors that affect the strength of the dispersion forces is the size of the molecule. So if you look at the first group, halogens, as we go down the group of halogens, you can see the molecular weight is increasing. But then look over one, the boiling point is increasing as well. So boiling point tells us a lot about the strength of intermolecular forces. The higher the boiling point, the stronger the intermolecular forces. So make sure to write that down. The higher the boiling point, the stronger the intermolecular forces. So as I go down the group and the molecular weights get bigger, the boiling point gets higher. That means the bigger my molecule, the stronger those intermolecular forces are. Same thing happens with the noble gases. Okay, as we go down the group, the noble gases are getting bigger, and those boiling points are getting bigger. So molecular weight plays a huge role in the strength of the intermolecular forces. All I have to do is add up those weights to see who has the strongest dispersion forces. Here's another example. Okay, we have, let's see here, 1, 2, 3, 4, 5, 6 carbon atoms in this carbon chain on the left, and its boiling point is 68.7 degrees Celsius. And then on the right, we have 3 carbons in our carbon chain, and its boiling point is much lower, negative 42.1 degrees Celsius. So the molecule that's larger has a higher boiling point because it has stronger intermolecular forces. Also, the shape of the molecule plays a big role in the determining the strength of the dispersion forces. So let's say, I have this carbon chain right here, okay? And let's see, 1, 2, 3, 4, 5, 6, 7, okay? Well, so we have 7 carbons and the hydrogens, and we have 7 carbons over here, but they're all in a ring, okay? So here, with this long carbon chain, I have all this area to form dispersion forces. But on my ball of carbon, I just have this area right here. So the more surface area on my molecule, the stronger the dispersion forces because there's more areas to form those interactions. But if I have a molecule that's all balled up, then I don't have that much surface area and they're not going to be as strong. So the shape of the molecule also plays a role. But honestly, it kind of goes along with the size of our molecule, right? The bigger the molecule, the more surface area. So the stronger our